Hello everyone, let's analyze. So in the last lecture we learned about what differentiability means, which of course we knew before, but now we have a more rigorous tool set to approach the question. Well, what does differentiability have to do with continuity? Well, I'll tell you. Suppose that f is a mapping from D to R and f is differentiable at some point C in its domain. Then f is continuous at C. Now, just so that we're on the same page, differentiability at a point implies continuity. But the converse is not true. Continuity does not imply differentiability. In fact, from the very last lecture, we know that the absolute value function is not differentiable at 0, but it is continuous at 0. So let's prove the statement. For every x in the domain not equal to c, we can write f of x as x minus c times f of x minus f of c over x minus c plus f of c. That's this statement here. Now you notice that this ratio here is a secant slope. But of course, if I were to cancel out x minus c and x minus c, negative f of c plus f of c, the only thing left standing would be f of x, which is what this is equal to. Now since f prime of c exists, and remember, what is f prime of c? Well, it's the limit of the secant slope function as x approaches c. So if I take the limit as x approaches c of f of x by applying the limit to this, then I get the limit as x approaches c of x minus c, which is of course 0. This is the derivative, which means it's a number. And this is f of x. I'm sorry, f of c. Now, let's be very careful here. This f of c is independent of x. Okay? We're trying to show that the limit of f of x as x approaches c is f of c. So we're not assuming the conclusion here. F of c is a constant, right? The variable is f of x and the variable name is x. So this is a constant. So if I take the limit as x approaches c of a constant, I just get that constant, f of c. So a function is continuous at an accumulation point c. Now, by the way, why is c an accumulation point? We haven't said that it is. Well, we know it has to be because the hypothesis of the statement is that f is differentiable at c. In order for f to be differentiable at c, by definition, c has to be an accumulation point. So, a function is continuous at an accumulation point c if and only if the limit as x approaches c of f of x exists and is equal to f of c, which is exactly what we just showed. Therefore, f of x is continuous at c, and, well, anywhere else that f is differentiable. Now, I know what you're thinking. What about the product rule? What about the quotient rule? What about the low D high minus high D low over low low? You all remember that, don't you? What about the fact that you could distribute the derivative across sums? Well, all these things are true. Of course, you knew they were true, but perhaps you hadn't rigorously proved it. So here we will. Well, actually, we'll prove the product rule. The quotient rule, you can find the proof of in your book. And of course, the summation rule just comes by the fact that limits can be distributed across sums when the limits exist. So, let's prove the product rule. let's take the derivative of f of x times g of x with respect to x. Well, that means we need to take the limit of the secant slope, right, as the width of the secant slope goes to 0. In other words, take the limit as x approaches c. C is where we're computing a derivative. F of x times g of x minus f of c times g of c over x minus c. And then we're going to add 0. So again, we're assuming that x is not equal to c. So we're going to add 0 to the numerator by adding f of x times g of c and subtracting f of x minus g of c. And then we can take this fraction and split it. And since these two terms both have an f of x in it, I can factor it out. These two terms both have a g of c in it, so I can factor it out. And because I know that g is differentiable at c and f is differentiable at c by hypothesis, as I take the limit as x approaches c, I get f of c. Now, by the way, how do I know that the limit as x approaches c of f of x is f of c? Well, I know that f is continuous at c. How do I know f is continuous at c? We proved it in the previous theorem, because I know that f is differentiable at c. This limit would be the derivative of g at c, which we know exists. This is, of course, g of c, so it's constant with respect to x. And this is the derivative of f. So I get exactly the chain rule. So again, for the summation rule, it's just a matter of distributing a limit, which we know from our arithmetical limits we're allowed to do. And the quotient rule, well, I'll refer you to the textbook for that. Now, another important derivative rule is the power rule. What's the derivative of x to the n? So let n be an integer, and let f of x equal x to the n. Then f prime of x equals n times x to the n minus 1. And that's true for all x if n is positive, rather a positive integer specifically, and it's true for all x except 0 if n is 0 or negative. So let's prove the case where n is a positive integer, and we'll do it by induction. Let's take the base case of n equals 1. We'll take the derivative of f of x equals x. It's pretty straightforward because once we apply the limit of secant slope, I just get x minus c divided by x minus c, which, so long as x is not c, is just 1. And the limit of 1 as x approaches c is, well, 1. Which, x to the 1, right? X to the 1, the derivative is 1 times x to the 0, which is, well, 1 times 1. Now for the inductive step, assume the result holds for n less than or equal to k. Right? And of course we know it holds for n equals 1. We want to show if it holds for any n, it holds for the next n. Meaning since it holds for 1, it holds for 2. Since it holds for 2, it holds for 3. So forth and so on, forever and ever and ever. So, suppose that for each integer, that for an integer n, the derivative of x to the n is n times x to the n minus 1. And now let's consider the function g of x equals x to the k plus 1. Which is, of course, x to the k times x. So we know that g is differentiable, so we can take the derivative using the product rule. Right, it's the derivative of x to the k times x, which would be the derivative of x to the k x to the k minus 1, times x plus x to the k times the derivative of x, which is 1. Of course, x to the k minus 1 times x, that's x to the k. So k times x to the k plus x to the k is k plus 1 times x to the k. So therefore, when n is k plus 1, the result holds. Now let's consider negative n, meaning n is equal to negative the absolute value. So we can apply the quotient rule along with a. In other words, x to the n is x to the negative absolute value of n, because n is negative, which is 1 over x to the n. And well, I can apply the quotient rule to that. Quotient rule would give me low d high minus high d low. Now, by the way, I know what the derivative of the denominator is, because we already know what the derivative of x to a positive integer is. We just proved that. Divided by low. I do my arithmetic, and I get the derivative is n times x to the n minus 1, because negative absolute value of n is n. The absolute value of n minus 2 times the absolute value n is negative absolute value of n, which is positive n. Again, I refer you to this statement here. Now, it only remains to show the case of n equals to 0. We showed positive n, negative n. Now for the 0 integer, f of x equals x to the 0, which is 1, except when x is 0. Now, here we get into a bit of a gray area. Why is 0 to the 0 not 1? Well, what is 0 to the 0? We often think that every number to the 0th power is 1, but we also think that 0 raised to every power is 0. So, when these two ideas collide in 0 to the 0, what is it? Well, in fact, in some contexts, 0 to the 0 is 1. In some contexts, 0 to the 0 is thought to be 0, and in some contexts, 0 to the 0 is thought to be undefined. So for here, we'll take it as undefined. And since it's undefined, 0 is not in the domain. But everywhere else, f of x equals to 1, which means our secant slope is 0 everywhere. And if I take the limit of 0, of course I just get 0. Now, if n were not an integer, the power rule still holds, but we would have to use some different machinery. Typically, the binomial theorem is used in that case. Now, we're at the end of the lecture, but one takeaway that's quite important is that differentiability is a stronger result. It's more than continuity. You can have a function that is continuous at a point, but not differentiable. Again, the absolute value is an example of that. Differentiability is something more. There's a layer of smoothness to the function that you have that continuity alone doesn't imply. Well, that's all for today.